but they are only, like you need it for each and some array dimensions. But normally you only have one opcode line per opcode. And one very nice thing that is often not removed by cryptos, by the easy cryptos, is there's also, for every opcode, there's a field that stores the exact PHP source code line number this opcode was compiled from. Sometimes it doesn't work. If you have a statement that spans across several lines, then it doesn't work. Then you have only the last line in this number. But usually it works. So you know this opcode is from line 5 in the PHP file, so then you can look in the source if you have the source code. So something to the about the operands. In PHP, which is very important, there are 5 different operand types. First there's the const operand type, which is for constant values, like never changing things in the source code, like a defined string, a defined number, or something else, or a defined array. So these cannot change. So if you see them somewhere in the bytecode, you know that this cannot be user input because it's always a constant. The next thing is there are so-called temporary variables. These are for storing intermediate results of multiplications, additions, concatenations, and all the intermediate variables used by the engine. Then you have an operand type which is called var. These are the variables. So these variables are like references to real PHP variables. So when you see this kind of operand used, it's usually the reference to a real PHP variable. With PHP 5.1, there was a new type introduced, which is the CV, the compiled variable type, and this is basically the same like the var type, with the difference that simple local variables in a scope, they usually don't need to be looked up every time you access them. And earlier PHP versions, when you accessed, for example, the very long variable name variable, then every time you access them, every time you add something to it, every time you use it, PHP needs to look up this very long name in the table. And to speed this up, there was introduced a new type of variable, which is the compiled variable. So now PHP knows this is like the variable with index 5. And so now when in the opcode there's only stored I'm a compiled variable with index 5. So PHP doesn't need to look up the very long name. It just needs to look up index 5 in its own table, and then it knows where the variable is. This resulted in a very huge speed up between PHP 5.0 and 5.1. And last but not least, sometimes operands are just unused, which doesn't mean they are really unused. They just mean they are not one of the 4 I just mentioned. They are just not defined by the 4 previous ones. So this is actually everything you need to know about PHP bytecode. And after the bytecode is compiled, it will get passed to the executor. And the executor is very different in different PHP versions. In PHP 4, it was like one very large function with a lot of cases of a switch statement. And so it was one very large function that contained all the engine in it. And then with PHP 5, it was introduced that every opcode got an own handler function. So the executor just loops through the op lines and calls the handler. With PHP 5.1, with the introduction of the CV variables, another speed up was introduced. So now we have not 1 but 25 opcode handlers per opcode. So that PHP knows there are 2 operands, and now it knows the first one is a CV, and the second one is like unused. So then it can calculate which of the 25 one it needs to call. And there's a speed up because now every opcode handler doesn't need to look up, is this a CV, then I need to access the variable this way. If it's a var, I need to access this variable this way. So now it actually can access it directly in the correct way, and this results in another speed up, which is very helpful for unpacking PHP, but you will see this later. So I already said for every combination of operands there are 5 different, for every combination of the 5 operands there's one opcode handler. So let's get back to the encryption. When I started working on the PHP bytecode encryptors, I was like, I'm lazy, I don't want to do it individually for every crypto. I worked on runtime encryptions during the days of DOS and early Windows cryptors, and so I knew that every time you crack a crypto, you just start a cat and mouse game. The vendor will change a few bits, and suddenly your unpacker doesn't work anymore, and you have work again. So it's a very time-consuming thing, and I want to spend my time on other things. So I didn't want to do reverse engineering on every new version of SendGuard or IronCube, and so I searched for a generic way to remove the bytecode encryptors. And therefore I searched weaknesses within the current bytecode encryptors. Like I already said, in the older cryptors, you had it that you had the hook of the compile function, and this hook just decrypted all the bytecode and then gave it to the original execute function and executed the bytecode by PHP. The problem with that is, at this point, of course, the bytecode is completely decrypted, so you don't need to do anything anymore. You just hook the send execute function and you get the decrypted bytecode for free. So you can do anything you want on this bytecode after that. And the other thing is the older cryptors, because they do not replace the executor, they cannot use obfuscation. Because if they want to do obfuscation, they need to hook within the engine so that some of their tricks still work. And right now, they don't do this. Well, actually, it would be possible, but they don't do it. They just decrypt everything and are ready. The modern cryptors, on the other hand, are completely different. The modern cryptors, they first try to obfuscate everything, and then they replace the executor. The good thing is, when you have a PHP application, you often have a large part which is the core, and the vendor doesn't want you to look into it and to change it. And then you have a lot of modules on the outside. The problem is, when you have modules on the outside, they are source code. And it's impossible to have obfuscated core with plain text modules on the outside, because the modules on the outside need to communicate with the core. And so if you obfuscate the core, the modules cannot access the core anymore. And therefore, most of the PHP applications, they are not encrypted with obfuscation activated. So usually most of these applications are not obfuscated at all. And therefore, removing the bytecode encryption is very easy. And even if you cannot deobfuscate, because it's obfuscated, the thing is, for security analysis, you don't want the original source code. You don't need all the fancy variable names. They might help you, but you don't need them to do security analysis. So most of the cases, you don't care. The other thing is, this is the biggest weakness of the current encryptors, is they are also very lazy people. So they just steal PHP source code. Well, they use it, it's not stolen because it's allowed by the license, but they just take the original executor, just copy it, they just change a few things, and they just use the original executor, which means it works exactly the same like the internal PHP executor, which also means they have the same very large opcode table in memory with 25 handlers per opcode. And we will use that for the generic decryption. The idea I came up with to create a generic unpacker was very simple. The idea was, I know the encryptor tool, the optimizer, for example, or the IronCube loader is loaded in memory. So somewhere in memory there must be the opcode table, the handler table. And so the first thing I do in the decryptor is to search this handler table in memory. How I do this, I will tell later. And then I replace all the opcodes in there, which is 25 times 150. I replace them all with so-called recording handlers. And then I just execute the PHP file as normally, but it's nothing executed, it's just recorded. And after that, I repair the op array and dump the op array everywhere I need, or store them for further analysis, or just print out the disassembly, whatever I want to do. So how do I find the opcode table? It's very simple. First, I start at the address of the replacement send execute form function, because I know this is a function, this is an address within the code segment of the optimizer or the IronCube loader. I also know that the data segment is loaded directly after the code segment with these dynamic libraries, and so I can just start scanning from the code pointer downward in the memory, and or upward, depending on how you like it. And then I search for this structure in memory. And actually finding the structure in memory is very simple, because I know it's aligned in memory. That means the bytes before will always be null. So I search for a single null pointer and then for something else. And this something else is, I know that there are 25 opcode handlers per opcode. So the first opcode is an NOP opcode. And there are no different types to implement a NOP opcode. So every one of these 25 opcode handlers is the same. So I just search for a null pointer followed by 25, the same pointer in the code segment, and then followed by something different, which is not the same pointer. And by using this simple heuristic, I never found a false positive, so I always found the real opcode handler in memory, and from that I can work further. So the next problem is to detect the end of the opcode table. I already told you I'm lazy, so I don't detect that. I just know that SendGuard just replaces 150 or 51 opcodes. So for SendGuard it's always 151. For IronCube it's like 255, and Source Guardian they don't need this. So for now I only have these two very hard cryptors like SendGuard and IronCube encoder, and so I only need two hard-coded values, and maybe when there are new cryptors that use this functionality, I will try and write an automatic detection. The next thing is I just back up the original table into some of my own memory, and then I replace it with recording handlers. And these recording handlers just record the decrypted operands. When the moment the opcode handler is called, it gets called with the decrypted operands by the cryptors. So I just record what I see. I see, oh, I was a recording handler for opcode 5, and this is operand 1, this is operand 2, and these are the other operands or special flags. And then I just continue with the next opcode line. And I repeat this through all op arrays, through all methods, to all functions, and I trigger the execution of every bit of PHP code I see in the encrypted file, and I just store the decrypted op arrays in some memory place, or later I dump it to the disk. And after I'm ready with that, I just restore the backup of the opcode handlers to from my own memory to the table. And when I'm lucky, I survived this whole process without a segmentation fault. Sometimes this results in a segmentation fault. I still don't know why. But usually it works when you have like 4,000 encrypted files. Maybe 10 are crashing the interpreter. And so until now, I didn't need to really find out why it sometimes crashes. after I have the decrypted opcode array, there's a problem, because some of these encryptors, they also optimize the bytecode. And when they optimize the bytecode, they